Uh, well, continue on. As I put out announcements, chapter one I posted up on Canvas. So just make sure you take a look at it. It's not very long, not very much out of there. You really have to worry about. As we talked about last time, it essentially is going to be chapter two is really the main kind of start here. And we got into it here. So we started talking about units last time, and again, sort of the importance of units. And remember that any type of measurement that you have should have units associated with it. It gives the person, again, a understanding of what that value represents. So as we talked about before, if you just write a number down like 55, who again knows really what that represents, what that means. We need some type of unit there to give us that sort of understanding of the actual value that is present. So you should always, as I mentioned last time, get into the habit of recording units, always with measurements, and you should always have units in your calculations, as we talked about before. We talked about towards the end there last time, there's really two types of units that we come across. One sort of the English units, which is again what we kind of use here in the US, and pretty much again everybody else uses the metric system. And they sort of got together and came up with, in chemistry and sciences, a standardized sort of system of units, which is referred to as the SI system of units. It really is sort of based off the metric system. So again, as we talked about, you'll see a lot, especially in the first several chapters, they'll talk about the SI unit of mass, the SI unit of volume, and so forth, are these different sort of values. It is also important, as we talked about, to understand what the units represent in terms of what type of quantity you're dealing with. So again, if you're talking about grams, you're talking about a mass. If you're talking about something like centimeters, you're talking about a length. So it's important to have that sort of recognition of it. In the metric system and so forth, we oftentimes will use prefixes, as we talked about last time, to sort of change the meaning of the value, or sometimes they're just measured in that. So again, if you had something like kilo, as we saw, which was 10 to the 3, remember that this is, again, as we will talk a little bit more about in this chapter, written in scientific notation. That's basically 1 times 10 to the 3, or 1,000 basically. And the way that you want to use that, as we talked about before, very commonly people do so always screw that up pretty good. They always kind of go backwards on this sort of conversion. So you could write in equality for kilograms again and grams, as we talked about. And remember that when you're doing this, there should always be what is sometimes referred to as the base unit, and that's the unit that's in both of the sort of values there. So obviously in this case, grams is the base unit here. Kilograms would be the prefix sort of unit. And when we look at that 10 to the 3, what that really represents is in one of the prefix unit always, that's how much of the base unit that we have. So that is always sort of the way that you want to use that. As I mentioned, definitely people always want to kind of do it the opposite way and do kind of 10 to the 3 kilograms in a gram and stuff like that. So you want to make sure that you are using it correctly. We'll talk more about it in this chapter, but a reminder, as we touched upon a little bit as a preview, again, this is what is referred to as an equality. An equality, again, is basically two values that represent the same amount of something, but they're on different units. So 1 kilogram and 1,000 grams represents the same mass. They're just on different units. And as we also touched upon, we can write conversion factors for those. 1 kilogram over 10 to the 3 grams, or 10 to the 3 grams over 1 kilogram. And again, these are our conversion factors, and they're really just fractions of the two values there. And they're used a lot, as we talked about at the very, very end there, in the type of calculation that we do a lot in chemistry, which is dimensional analysis. And we use dimensional analysis to show our work, to set up problems. This basically shows units canceling units. So again, if we had something like 5 kilograms and we want to know how many grams that was, we think of it kind of as fractions, and we set up dimensional analysis so that opposites cancel. Thank you very much. And again, the only kind of three things you have to remember when you do dimensional analysis, as we'll talk about later on this chapter, is opposites cancel and things on top get multiplied, things on the bottom get divided. Those are three things basically all you have to remember. So here we would want to choose the conversion factor where the kilograms in the opposite location, so it's up on top. We would want it on the bottom in this case to cancel. And that way, when we multiply and when we divide, the kilograms here will cancel, and we'll basically get something like 5,000 grams in this particular case. So that is a very short sort of dimensional analysis setup, but it's a really important sort of calculation, and we'll go officially into that. And as I mentioned before, in chemistry, when they say show your work, that's essentially how they want you to kind of show your work. You need to set it up that way with the units and making sure everything cancels out, which again is why it's really, really important, obviously, to have units all through your calculations, not just numbers. And it's also very beneficial to you. As I mentioned last time, and which we'll talk about more this time, again, you can essentially a lot of times not even have to worry about a formula. If you just kind of take a dimensional analysis approach to a problem, it will kind of do the math for you, it'll do the rearranging for you, and it's very helpful sometimes along the way. Any questions on any of that stuff we talked about last time? All right, then let us continue on. That is a ruler, and on a ruler here, we have our 1 inch, which is our English unit. And if we come down, that is 2.54 centimeters, which is our metric. Definitely, this is one of those equalities that they expect you to know, that 1 inch is exactly 2.54 centimeters. That is, again, definitely something that you do need to know. By the way, just a reminder, when we're looking at our ruler here, again, up on top is inches. The big numbers here are centimeters. The smaller little dashes are, what are they? They're millimeters. Yeah, so those are millimeters, the little guys there. There are 10 millimeters in a centimeter, so those are millimeters there. So using a ruler, taking proper measurements, we're going to talk about. And you want to make sure, obviously, you're taking it in the proper units. If you need inches or centimeters or millimeters. So let's talk a little bit about some common volume sort of conversions. Volume is the amount of space, three-dimensional space is occupied by a substance. The volume, SI unit, is length cubed, and that basically is meters cubed, and that actually is a volume. And there's a few different sort of relationships. 1 decimeter cubed is a liter. This relationship here is one that is used a lot, and obviously you do need to know. 1 centimeter cubed is equal to 1 milliliter, so it is a 1-to-1 conversion. Now you may be saying to yourself, isn't centimeters a unit of length? And it is, and one way that you could get a volume of something, say like a cube, is you could take length times width times height. And if you were going to measure all those things, you would measure all those things in, say, centimeters, which each of these individual measurements here, they are all length measurements. But if you multiply them together, you will end up with cubic centimeters, which represents a volume. So each of these individual guys here are all length measurements. But if you take 3 length measurements in those sort of orientations, multiply them together, you will get a cubic centimeter, which represents a volume. So if you have any type of length measurement that's been cubed, is actually referring to a volume and is not referring to length or distance or anything like that. In addition, probably more often than not, that right there is definitely one that you will use a lot. 1 liter is equal to 1,000 milliliters. We use that conversion a lot in chemistry. Oftentimes in the laboratory or when you take actual measurements, oftentimes they are given in milliliters or you take the measurement in milliliters. But in a lot of sort of formulas in chemistry, the volume needs to be in liters for everything to cancel out. So kind of going back and forth from liters to milliliters or liters or milliliters to liters is a really, really common sort of calculation. We'll see it as well, I think, in a bit, but also 1 cubic centimeter is 1 milliliter. A cubic centimeter is also sometimes referred to as a cc, and that is a cubic centimeter. A lot of times they use that in medicine, right? Give the guy 5 cc's of this before he dies, right? And it's basically a cubic centimeter, or a milliliter is basically what they're using there. Any questions on that there? Now, mass is the amount of quantity of matter that is present in an object. Matter is basically anything that has mass and occupies space, so it's pretty much everything. We have 3 states of matter, as we'll talk about in another chapter, but typically we have solid, right, liquid, and gas, and those are the 3 sort of states of matter that we come across. The fundamental SI unit there for mass is a kilogram, and that is a common unit in chemistry that is used. This relationship here of 1 kilogram is 1,000 grams is definitely one that comes up a lot. Also, milligrams. There are 1,000, for example, milligrams in 1 gram. Milli is 10 to the minus 3, so is a smaller unit, so there's a lot more of it in it. And I would say those are 2 very common sort of mass conversions. I'd say most of the time we deal with grams is a very common unit in the laboratory. Those balances in the back of the room, and most balances do give the measurement there in grams. But kilograms does pop up a lot. And obviously, again, these are more metric SI sort of units. And for example, when you go to doctor, oftentimes they give your weight there in kilograms, right? They kind of use that as the unit. Now, there is a difference between weight and mass, and sometimes they're used interchangeably, but there actually is sort of a difference between those 2 things. Weight takes into account and is affected by the force of gravity, where mass is not. So if you had an apple, the weight of the apple here versus the weight of the apple, say, on the moon, would be different because there's only 1/6 of the force of gravity down up there as versus here. And the mass, though, of the object would be the same in both places. So when we do weigh something, which is oftentimes why people get confused by that, because obviously when you put something on the balance, you're doing the process of weighing something. So oftentimes people call it the weight. We actually are getting the mass of it. Believe it or not, the mass, the balances and stuff like that are programmed to sort of take out the force of gravity in the way they're sort of designed. And so in chemistry, when we do weigh something, you should refer to it as the mass of an object rather than the weight of an object, as the force of gravity, again, is sort of taken out. And that is sort of universal no matter where you're at. So let's talk a little about temperature and temperature conversions. And again, you do need to know these 3 temperature scales. Let's come back here. And there's really 3 temperature scales that we come across. There is degrees Fahrenheit. There's degrees Celsius. And again, there's one that you may not be extremely familiar with yet, but it is Kelvin. And one of the first sort of differences between the 3 units there of temperature is, as you can see there, when you do write Kelvin as a unit, It is not degrees Kelvin. So we don't use the degree symbol. We don't say degrees. We just basically say the number and Kelvin. So 273 Kelvin would be the temperature. We don't say 273 degrees Kelvin. So we don't use the degrees sign with that. The other two we definitely do. Fahrenheit scale. Water boils at 212 degrees Fahrenheit, freezes at 32. That is the one we're very common with. We take our temperature, right? Temperature outside, right? We do all the Fahrenheit type things. And that is typically used here. Um, the Celsius scale, which is a metric system, water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. That right there is definitely two numbers that you should know. Yeah. And they come up a lot. Um, the boiling point of water, also the freezing point or melting point of water, as well, 0 degrees Celsius. Third one, as I mentioned before, used to be called the absolute temperature scale. It was later renamed for our friend there, Kelvin, assuming that's why they call it that. And that is really, honestly, the major temperature scale that we use in chemistry. Pretty much, if it is a chemical formula that you need to calculate, if you got temperature involved in there, pretty almost automatic. You got to convert it to Kelvin. It's like should be just like an automatic thing. I need to put that thing in Kelvin. There's only one probably formula that we will see in the entire semester and probably in your whole chemistry career that you actually leave it in Celsius. So pretty much 99.99% of the time it's going to be rolling into Kelvin. So again, it should just sort of be an automatic sort of conversion. What's the deal with degrees Fahrenheit? Well, they include it, but I would say probably after this chapter, you probably won't see too much Fahrenheit in your chemistry life. These are the big two. And the conversion between degrees Celsius to Kelvin is probably the one you'll do the most. And taking it back from Kelvin to degrees Celsius is probably the second one that you do the most. So kind of going between those two units is very common sort of conversions that we do here in chemistry. In the laboratory, your thermometers that you checked in with, it's degrees Celsius on those thermometers. So it's very common in the lab. We take temperature readings in Celsius. And like I said, you typically do have to convert it to Kelvin when you put it into a formula. Now, to convert between these three different temperature scales, it's really based on where the boiling point and the freezing point of water is. Sort of the difference between them is how we kind of do the conversion. There's about 180 degree difference on the Fahrenheit scale between sort of freezing and boiling. On the Celsius and Kelvin scale, there's about 100 difference on these two, about 100 difference. And here there's degree difference between them. And that's sort of what's going to make up basically our conversion. So let's talk about how we do convert them. And clearly they're in a box, which means you do need to know them. And we'll talk about the first one here, which is probably the one that you're going to use the most. And I'm just going to scratch it out here for just a second because here they're very, very specific as to what they want you to know. Outside of this college, probably when you do this conversion, most people will use the number 273. But here, as you might imagine, they would like you to do it specifically. So to convert to the temperature in Kelvin, you take the temperature in Celsius and you add 273.15. So they do want you to keep the 0.15 here at this college. I would say outside this college, nobody keeps the 0.15, but here they would like you to do that. So we will do that. You may even see it rounded here in some labs to 273.2, but 273.15 we will roll with. So you do need to do that. Like I said, very commonly outside of here, people just go with 273. A lot of cases, that last part gets a little bit rounded off anyways, but we will keep it here. So this probably is 99.9% of the time what you're going to do. Obviously, if you need to go back the other way, you're going to take to get your temperature in Celsius, you're you're going to take your temperature in Kelvin and minus 273.15. So you're just going to do the opposite calculation there. And those pretty much outside of this chapter, like I mentioned, are going to be pretty much your conversions for temperature. Those are going to be the ones definitely, if you got to lock it in, which you do in this school, you should definitely lock those two in there because it's going to be the ones going to pop up the most. Now, to convert between Fahrenheit and Celsius, you could take the temperature in Fahrenheit is 1.8 times the temperature in Celsius plus 32. That 1.8 number is the same as maybe a fraction that you learned, 9 over 5. It will give you that 1.8. And you can use 9 over 5. Sometimes people use that as well. If you need the temperature in Celsius, you're going to take the temperature in Fahrenheit minus 32 divided by 1.8. So all of these you should know for sure. Again, they will not be provided for you here. But outside of this chapter, these are pretty much the ones you should, really lock in because they're going to be the ones you're going to use the most. Obviously, in this case, if you have the temperature in Fahrenheit and you want Kelvin, you need to first take it from Fahrenheit and convert it to Celsius, and then take it from Celsius and convert it to Kelvin. Same idea as well. If you're starting in Kelvin and you want to go all the way down to Fahrenheit, you got to take it from Kelvin to Celsius, Celsius to Fahrenheit. So you kind of have to go all three of them if you're going from one extreme to the next. Any questions on that there? So why don't we grab our calculators, give these three a go. Why don't you do these temperature conversions? Temperature is 28.5 degrees. What is it in Kelvin? We got 41 degrees on the second one. What is it in Fahrenheit? And 160 degrees Fahrenheit. What is it in Celsius? So take a few moments here and calculate each of these with your calculator there. Okay, let's take a look. So on the first one here, we really have Celsius, and we want to get to Kelvin. So we got basically degrees Celsius, and we want to end up on Kelvin. So our formula there is the temperature in Kelvin is the temperature in Celsius plus a 273. Again, they do want you to keep the 0.15, so we'll do that. So we'll pop our number in there. We'll go 28.5 plus 273.1, whoops, 15. And that is going to get us here. Looks like 301.65 there on our calculator. Now, when we do give answers, as we'll definitely talk about, we do want to give into the proper number of usually significant figures. The one place where we do not follow really strict significant figure rules is with temperature conversions. So if you're just simply doing kind of a temperature to temperature conversion, we don't really follow the normal significant figure rules that we'll talk about later on this chapter. So let's talk about the rule that we typically follow. If you're just doing a temperature to temperature conversion, we make our answer look like the original value. So in our case here, our original value went to 1 decimal place, which means that when we do this conversion, we would want to take it to 1 decimal place. So that will tell us where we want to go. So really, we would want to go here to the 6. As you may know, we'll talk a little bit about it as well. When you round, you look at the next number, right? In this case, it's 5 or above, which means we do round up, right? So we would end up with a 301.7 Kelvin. Once again, there is no degree sign on it. It is just Kelvin along the way. Any questions on that? And once again, this rule is specific for just temperature to temperature conversions. There's obviously real significant figure rules that we follow for everything else, but that is what we typically do here. On the next one, we're looking for Fahrenheit. So our temperature in Fahrenheit is 1.8 times the temperature in Celsius plus a 32, which means we got 1.8 times 41 plus 32. And that's going to get us here 1.8 times 41 plus a 32. On your calculator, you're going to end up with 105.6, 105.8. 105.8. Here we do use degrees Fahrenheit. And really the reason why we kind of do our general rounding rule here with temperature is actually for like this conversion and the other conversion. Here we use 1.80. Some people will use just 1.8. Some people will use the fraction 9/5. So there's a lot of variance that could happen if you try to follow strict significant figure rules with temperature. Everybody might follow something different depending on what conversion they sort of use. So once again here, we're just going to look at the original number. That is a whole number in this case, which means we would round this to our whole number, which means we would round up to 106 degrees Fahrenheit. Yeah. Any questions on that one there? Lastly here, we're going from Fahrenheit to Celsius, so our temperature in Celsius, temperature in Fahrenheit minus 32 divided by 1.8 gets us a 160 minus 32 divided by 1.8. I feel like that's a lot of ones in this answer here. Let's see. So on your calculator there, you're going to get 71.11, a bunch of ones. Degrees Celsius. Once again here, looking at our original number, also a whole number, we would come to here, we would look at this number, and in this case, we just drop the rest of them, and 71 degrees Celsius would be our answer in this case. Any questions on temperature conversion? So clearly, you do need to know how to do them. You do need to make sure you clean up your temperature conversion following kind of that general rule. And like I said before, Kelvin to Celsius, Celsius Kelvin, probably most often what you're going to be doing. Yeah. Any questions? All right. So here we want to, as I mentioned before, understand the type of unit we're taking or measurement. So obviously here, if I have Kelvin, that is what type of measurement? That is measuring temperature, right? Liters is measuring, maybe I'll spit that out, volume, there it is. Meters is length, right, or distance, and kilograms should be mass. So as we talked about last time, right, it's important to understand that and what those units represent. All right, so let's talk a little bit about a couple of types of measurements, if you will, or not really measurements, but really observations. So there's qualitative and there's quantitative. Qualitative basically consists of general observations about something. It's green, there was bubbles, a solid formed. It's really, when you do qualitative, there's really no measurements that occur there. So qualitative is just general observations, no measurements. Yeah. So you will, if you go to 1B, do a bunch of experiments, which are known as qualitative analysis experiments. And those experiments, you do nothing, no measurements. You don't measure out how much solution. You just go, like 4 drops looks good, or 10 drops works. You don't really measure it. You just take a lot of observations. A lot of the outcomes of those experiments, for example, are just like colors you see, solids that are formed. There's no real measurements. When we talk about measurements, we're talking about quantitative, and quantitative pretty much is all about measurements and taking a measurement. So when you take something to the balance and you weigh it and it says it's 55.562 grams, that is a quantitative measurement. When you transfer a certain amount of water and make sure that you do it correctly, use something like a pipette that's like a 5 milliliter pipette, you are quantitatively transferring that. You're not just kind of pouring it by hand and go, it's about 5, right? So you're quantitatively transferring those liquids. So anything that is measured is a quantitative, consists of numbers, consists of units and values. Now, when we deal with numbers, as you may be familiar with or not familiar with, Let's talk about scientific notation a little bit here before we go too far. Scientific notation is oftentimes used to handle really big numbers and really small numbers. So as you can see there, you got a number like 602200000, lots of zeros, and point a ton of zeros, 166. Odds are, if you try to keep it in positional notation or decimal point form, if you will, you're going to lose some zeros or many zeros there along the way as you try to do those calculations. So to handle these numbers, we use scientific notation, and scientific notation is written a certain way. It is n times 10 to the n, and this n is a number between 1 and 10. So it cannot really be 10, it cannot be higher than 10. It can be 1 though. 1's okay. It can't be less than 1. So you could have a number that's 1. You can't really have a number that's 10. You got to have 9 point something. And it's times 10 to the n. This number here is a whole number that's either positive or negative, depending on really how many places you need to move your decimal point to get to a number between 1 and 10, and which way you need to move it to do so. So if I had something like 1, 2, 5, 6, and I wanted to write it in scientific notation, although it is not written into the number, we do assume that the decimal point's over here at the end, and we would need to go one place to the right if I do the, or to the left there, one place to the left. If I do that, that's 125.6. That definitely is not a number between 1 and 10. I go one more place, that's 12.56. That is still not a number between 1 and 10. I need to go one more place. And that will give me a number of 1.256 times 10 to the 3 as I move the decimal place 3 places to the left. And that is what the 3 on top represents. It is a positive number if your original number is a large number, is a good way to remember it. So anything above 1 is typically a positive exponent, or you move the decimal point to the left. Now, if I had something like 0.00120, here I would need to go one place to the right, that's 0.0, 2 places to the right, that's 0.1. That is not a number between 1 and 10. I need to go one more place. And that will give me 1.20 times 10 to the minus 3 in this case. Again, the 3 represents how many places I had to go to get to a number between 1 and 10. The negative in this case means I had to move the decimal place to the right. Or again, if you want to remember it, small numbers, negative exponents, larger numbers, positive exponents. Any questions on that there? Do you always have to give your answer in scientific notation? The answer is no, but sometimes the only way to give an answer to the correct number, for example, of significant figures, which we'll talk about, is to write it in scientific notation. So why is that? When you look at a number that is in scientific notation or written in scientific notation, we'll just take this one. When you look at that number, any number that comes before the times 10 part, so any of those numbers that come before the times 10 part of the number are significant figures, and they're important numbers and digits. So all of those numbers in this particular case here are significant figures. And in this case, this number would have obviously 3 significant figures the way that is written. By the way, as we'll talk a little bit more about as well, people sometimes, when they're asked a question of like how many significant figures does this number have, and it's written in scientific notation, they want to convert it out of scientific notation and then try to figure out how many significant figures it has. Not a good idea. It's written in scientific notation with those amount of numbers for a reason. It tells you right there how many significant figures it has. So if you have a number in scientific notation, you can just look at it and know for sure how many significant figures it has, as long as the person obviously wrote it correctly. That is how many significant figures that number has. So why do I say sometimes the only way you could give the answer is in scientific notation to get the correct one? Let's just say that we did a calculation. Obviously, we'll talk about the rules for how many significant figures your answer should have shortly. But let's just say we did the calculation and I don't really need 3 significant figures for my answer, but I actually only need 2. And that's not a problem because, frankly, I could just, instead of 1.20, write 1.2 times 10 to the minus 3. Now I have 2 significant figures. If I only needed 1 significant figure, I could just write 1 times 10 to the minus 3. Now I have 1 significant figure. So when you write a number in scientific notation, you could kind of dictate how many significant figures you're writing. And there are going to be some calculations you'll come across, not a lot, but occasionally it does pop up. You're like, oh, I need like 3 significant figures here. There's no way to write it in like decimal form and have 3 significant figures. I'm always going to have too many or too less. Scientific notation is the way that you have to kind of write it to get it to the right answer. If you want to write your numbers in scientific notation, perfectly fine. The only time you are required to do it is obviously if the question says make sure you give your answer in scientific notation. But you may just want to do, especially if you have really large numbers or really small numbers for answers. You don't want to have to write all those digits and stuff like that. Any questions on that? Now, more importantly than being able to sort of write scientific notation, you do need to be able to obviously write a number in scientific notation. You do need to be able to take it from scientific notation back to decimal form. And obviously, if you're doing that, you're just going to kind of go backwards. So if you did have something like 3.2 times 10 to the 3, the first thing you're going to know is, hopefully, when you look at this, that is a positive exponent, which means this number should be a bigger number, right? And if you're not sure which way you should move the decimal, you could just try. If I go this way, I'm now at like 0.3, right? That is definitely not a larger number. That's now a smaller number, right? So we don't want to do that. So in this case, we would need to go this way, 1, 2, and 3. And obviously, we would need to add some zeros here in those spots. And we would end up with 3,200 in this particular case. Now, again, if you had 4.2 times 10 to the minus 2, again, the negative here tells you it's going to be a small number, so you would move your decimal point to the left in this case, because by doing so, we're now becoming 0.4, right, which is making it smaller, right? We go one more place, 0.04, we're going to make it smaller in that case. So we'll end up with 0.042. Obviously, we need to go 2 places there, and we would convert it back here. So you do need to be able to kind of go in both directions. So make sure that you do know how to do that as well. But in addition to obviously knowing how to do that, what I was actually saying before is the more important thing is knowing how to properly use your calculator when you want to put a number in scientific notation. And for the most part, most people do not know how to properly do that, and they use all kinds of weird buttons on your calculator, and you'll end up with the wrong answer in a lot of cases. And what frustrates people usually is if you punch it into your calculator incorrectly, you will usually end up with an answer that's really close, but the exponent part of the number is wrong, and that's because you didn't enter it correctly. So we're going to talk about 2 types of calculators, and really, just in case you're in a different class, at least you'll know how to do it. But there's 2 types of calculators. There's kind of display calculators, and there's non-display calculators. And if you're not sure which one you have, you could just very simply hit the log button. And if your screen says log, you have a display calculator. And if your calculator says error, you have a non-display calculator. So since you're required to have a specific calculator for this class, when you hit log on your calculator, what does it say? It says error, right? So you have a non-display calculator. So as we go through the semester, we'll talk about how to punch it into that. But on most calculators, there's really three types of buttons, which are actually the exponent buttons. And if you look on your calculator, which is the one you're required to have, you have this EE button. And that is actually your exponent button. That is the button that you should use for scientific notation. I believe is somewhere center-ish, right above the numbers in that area on there. By the way, in case you have some other calculators at home or something like that, there are some other common exponent buttons. Some calculators will use an EXP button. And some of the newer calculators are kind of like two-tone. It's got like a solid color on the outside. A lot of times they're white and kind of a two-tone calculator. A lot of those will actually have a button that's like times 10 to the n type of button. And if you actually own one of those and you're using it for a different class, because you can't use it for this class, there's a lot of extra steps that you have to put into when you use that calculator. But we'll focus in on this one here. And the other button that's important is there's usually what I call kind of like your negative button. It's really like your change your sign button. And most calculators will have a plus negative, or some will have sort of that. It's not the subtract button. I think your calculator has the plus negative, or does it have the parentheses with the negative in it? Can I see yours real quick? Yeah, that's okay. I've looked at too many calculators to remember. Yeah. So on your guys' calculator right here, right underneath the 3 is your button. And it's kind of like the plus negative. It kind of looks like, I guess it's a plus to negative sort of button. Should be right underneath the 3 there on your calculator. Thank you. And that button is important as well because that will change the sign. Obviously, if you have a negative exponent or a positive exponent, you may have to hit that. So on your calculator, if you wanted to put a number in scientific notation, let's say we had 1.25 times 10 to the minus 3, you would want to punch 1.25 into your calculator. You then would want to hit that EE button. Now, depending on your calculator, I believe your calculator will just kind of move everything over to the right a little bit. Guys, bar real quick just to make sure. Yeah. Okay, got it. So when you hit your button on your display, it will look something like this, 1.25, and it'll kind of pop up a couple of zeros. And when you hit this button, that button represents the times 10 part of the number. So you should not hit the multiplication button. You should not hit any weird buttons like inverse log or anything like that unless you don't want the right answer. So when you hit this button, it represents this part of the number. That means that what you have left to punch in there is negative 3. So you would then hit your negative button, that one by the 3. Try to draw it like that. And then you're going to hit 3. And that should change your display to something that looks like this, probably. Yeah. And that will get you the proper way to punch in 1.25 times 10 to the negative 3. Again, you should not use any type of exponent or any type of multiplication button when you're doing that. Everybody get that? Yeah, on your calculator? Yeah. All right. So if you have a positive exponent, say you had 4.25 times 10 to the 4, you would do kind of the same thing. You would type 4.25. You would hit your exponent button. In this case, we do not have a negative, so when we hit that exponent button, it'll take care of that part, and you just hit 4, and on your screen, it probably looks something like this, maybe. And I don't think it puts a small little times 10 on the bottom or anything like that. I think it just pops the zeros up, I think. Any questions on how to do that? That is probably more important. Oh, let me see what's happening. Is it changing it into decimal form? Uh, okay. All right, so on your calculator, if it is not programmed to be in scientific notation, which it probably isn't out of the box, it will convert your number into a decimal or a regular number, which is perfectly fine. So on that one, what it will show up if it is not in scientific notation, you will end up with 4250000 on your thing. And the other one, it will probably move it to 0.125. And that's perfectly fine. Those are the right ones. What will happen, obviously, if you put in there something where your calculator only has so many spots. So if you put something where it can't do that, so why don't we do one where it will keep it in scientific notation? So if you put into your calculator 1.25 times 10 to the 24, and again, you would do 1.25, you'll hit your exponent button, and 24. It has no choice but to keep it in scientific notation because it doesn't have enough spots. Yeah. And this is really important. If you look at this 24, which is up on top, is the times 10 part of the number. So if you had to write that as your answer, you would want to write 1.25 times 10 to the 24. You don't want to just write the 1.25. You got to make sure you look for that. So we'll talk about it maybe next time as well. But if you want to put your calculator give your answer always in scientific notation, you can. If not, it will probably convert your numbers, it looks like, into regular numbers if it has enough space. If it doesn't have enough space, it will keep it as scientific notation. So when you look at your calculator that you need to use here, anytime you see a number after you get an answer and there's another like number towards the top, that is like the times 10 part of the number. Yeah. And you don't want to forget that. So again, if you saw something on your screen like that, this would be 1.25 times 10 to the 42. And a lot of people do forget that part of the number. This get like the front part, the big numbers. So you don't want to do that. If you have a negative exponent, it will probably look like I showed before, negative 0. Maybe let's go really big, 9. You would want to make sure you turn that properly into 3.25 times 10 to the minus 9. So you do not want to forget that. If you have an answer that has those little numbers up on top, that is a part of your answer that you need to give. Any questions on that there? Why don't we try a couple here? Maybe we'll get some answers that will make you do that here. Let's see. Do this. Let's do let's do 3.2 times 10 to the minus 3, and let's divide it by 4.65 times 10 to the 17. And let's also do 6.33 times 10 to the 5 times 7.2 times 10 to the minus 26. All right, so take your calculator, punch it in correctly using your exponent button, your negative button, and see what you get there. So again, if you're going to punch this in correctly, you want to punch in first 3.2. You then want to hit your exponent button. And again, that takes care of that part of the number by hitting that exponent button. This is a negative 3, so you want to hit your negative button. I'm just going to write it like this. And then you're going to hit 3. You're going to hit the divide button. And then you're going to punch this guy in the same way, 4.65. Once again, going to hit the exponent button. That's going to take care of that part of the number. This is a positive 17, and you're going to hit equals. If you do all that good stuff there, you will end up with some type of number on your calculator, maybe. Here you end up with an error if you punch it in wrong. Let's try it right. There you go. So I'm assuming on your calculator it will probably look like 6.8817204. Does it go all the way to 4? Yeah. You go to 3 as well. And you will probably have up on top a minus 21. Yeah. And again, when we would give this answer, we want to make sure we don't forget about the minus 21 part. By the way, the right answer here is something like 6.9 times 10 to the minus 21 if we follow significant figure rules, which we will think about. But when you're dividing, it's the smallest number of significant figures. And this guy has 2 significant figures. This one has 3 significant figures. The answer should have 2 significant figures. First off, any questions on that there? No, it's actually whichever one's smaller. We'll talk about the rules coming up, but that's why we round in this case to 6.9 in this case. Yeah. Other questions? Okay. Now, if you do the other one, you're going to punch it in very similar. You're going to go 6.33. Once again, you're going to hit your exponent button, which once again will represent that part of the number. And then you're just going to go 5 next. Going to hit your multiplication button, 7.2. Once again, exponent button, which will take care of that part there. And here we do have a negative, which means we will need our negative button there by the 3 and 26 and equals. And in this particular case here, we got 6.33 to the 5 times 7.2 to the negative 26. And again, on your calculator, you probably got probably these numbers here, 4.5576. Again, up on top is probably a negative 20, I hope, yeah. And once again, sig fig wise, and again, we'll talk more about it, but that's 3 sig figs. That's 2 sig figs. So we would actually round here to 4.6 times 10 to the minus 20. Once again, we do not want to forget that part of the number. It is very commonly forgotten when people look at calculators, especially on yours. It only kind of pops it up on top there. It doesn't really say times 10, I don't think. So sometimes, people kind of overlook it. Now, based on the way your calculator is programmed, if you did not put it to give you your answers always in scientific notation, if you come across a problem that you do put in scientific notation, the numbers, and the answer is in a number that it could actually fit on your screen, it probably will just give it to you in a regular number form. So you may not have that always. So let's just say we had, let's say we took 1.25 to the 2. Let's say we did this one, 1.25 times 10 to the 2, and we'll multiply it by 3.0. Whoops. We'll go 3.0 times 10 to the negative 1. So go ahead and pop that into your calculator properly. Okay, so again, we're going to punch it in 1.25. We're going to hit our exponent button. And that's a positive 2, so we don't need the negative, so just the 2. Going to hit the multiplication button, punch this in 3.0 exponent button. And this is a negative, so we do need the negative here and a 1 and hit equals. And in this case, you actually just get a small enough number that it will probably just spit out to you 37.5 in this case. And really we would round in normal situations to 38, but that's what you'll probably see on your calculator. It probably will not put it in scientific notation because it has enough digits to put on your screen. Like I said, you should be able to, if you really want everything in scientific notation, you can program probably the calculator to do that. I think maybe you might not want to do that because you might miss some of those exponents. So maybe just leave it in regular form there and just understand, when you do see those numbers up on top at the end, it is important. Don't disregard them. Yeah. Any questions on how to punch it into your calculator, which is probably more important than all the rest of it? No. 38 would actually be, and we'll talk about the rules for significant figures, but 38 would actually be, and it's again here we're multiplying. So the first number has 3 significant figures, second one has 2, so 2 significant figures at the end, which would be those 2. Other questions? Yeah. Here's some examples. When I get rid of everything I wrote on this. All right, so again, just some examples, moving numbers back to scientific notation. Here we do need to go to the left 2 places. So we have 5.68762 times 10 to the 2. Now you may be wondering, why are we keeping all those numbers? And the answer really does have to do with significant figures, as we'll talk about when we get there. But if you look at the top number, every single one of those numbers in the original number here, they're all significant. And that means when you turn it into scientific notation, you should not lose any significant figures along the way. So you do have to keep all these numbers, because this number up here has 6 significant figures. The number below it has 6 significant figures. If I wrote the number below it as 5.7 times 10 to the 2, how many significant figures would it have? It would only have 2, right? And now I just lost like 4 significant figures, and you shouldn't do that. So if you're taking a number from kind of decimal form to scientific notation or backwards, you do need to really maintain the proper number of significant figures. You shouldn't lose any along the way. Same thing here. We need to go to the right several places, 6 places to get to 7.7. 2 times 10 to the minus 6. Again, we'll talk about the rules for significant figures, but in this original number, just the 772 is significant. All those zeros are not significant. And that way, when we turn it into scientific notation here, we now have the same 3 significant figures in both of the numbers, and we maintain that. Here, 12,500, although the decimal point is not written, we assume it's there. 1, 2, 3, 4 places. That is where the 4 comes from. And we end up with 1.25 times 10 to the 4. And we'll talk about it, but here the zeros actually at the end are not significant. Only the 125 there, and that number is significant. So that's why we have 3 in each. And lastly, we would just go 1 place here. Gets us our 1.35 times 10 to the minus 1. So again, that's really important as well. You don't want to make sure you don't lose any significant figures along the way if you're just kind of turning a number into scientific notation or backwards. Any questions on any of that there? All right, we will lay that up for